Good evening to all of you, and welcome you all to the fourth day special guest lecture. And today we are very happy to have Shankho from IMSC Chennai, and he is going to have a very interesting discussion, it seems from the title, Collider Physics Plus Plus in Effective Field Theories, and then a highly, with a question mark, biased perspective. So with this, Shankho would like to start.
So before starting, I would like to thank Shubhoda for inviting me, and so I was last here during WEP in 2019, so it's always good to be back here. So the topic is very broad and very biased because I work on these areas. So we can get started. So because the topic is on collider physics, I'm going to talk a bit about colliders. So there have been colliders in the past which have discovered a lot of particles for us. So for example, there have been E plus E minus colliders like the SPHERE within the SLAC facility, which discovered the JSI meson along with BNL. Then Petra, which in DAISY, which discovered the gluon jets. LEP collider, which was at CERN, measured very precisely the mass of the weak bosons, the W and the Z bosons. So here you can see the LEP facility. On top of that, I'm not sure how clear the numbers are from back at the back. So LEP was able to constrain the Higgs boson mass even before its discovery. So LEP said that the mass of the Higgs boson should be more than 114.4 GeV. Then there were past proton-proton as well as proton-antiproton colliders. So ISR was the first PP collider. Then the SPS, which used to be an injector of the E plus E minus beams into the LEP collider and now acts as an injector to the L8C. So it used to be a collider on its own, and it discovered the W and the Z bosons. Tevatron was a PP bar collider in the US, and the top quark was discovered here. And apart from LEP, Tevatron was also able to put strong constraints on the Higgs boson. For instance, it said that the Higgs mass cannot be between 100 and 103 GeV and some 147 and 180 GeV. And in the BB bar final state, it was able to like not discover, but it saw an evidence of the Higgs boson between a mass of 115 and 140 GeV. So Tevatron was a very, very important machine, and recently you probably have heard about the W mass measurement controversy from recent analysis of Tevatron results. So on top of that, there was the fixed target facility at SLAC, which discovered the charm quark, the quark structure inside the protons and the neutrons, and it also discovered the tau lepton. So this is the LEP facility. It used to be at CERN. It used to be a 27-kilometer radius tunnel sprawling across Switzerland and France. And this same tunnel was taken over for the L8C. So L8C has many experiments, but there are 4 major experiments, the 2 general purpose detectors, ATLAS and CMS. Many of you have heard of these, and then L8CB and ALICE, but there are also many small experiments which I'm not going to talk about today. So L8C has been running since 2009 and discovered the Higgs boson in 2012, and since then they have been trying to precisely measure the properties of various standard model particles, as well as trying to find new physics directly. There is a present heavy ion collider, which is the RHIC. It has been running from 2000, and it studies quark-gluon plasma and physics of the early universe. So the second edition of it is going to be the electron-ion collider, which is going to be something very interesting. So now present E plus E minus collider in Japan, Super KEKB. So it has been running since 2018, and it made precise measurements, is still making precise measurements of B mesons. So future colliders. So again, this is a very, very interesting, as well as like we are not sure what's going to happen. So there are many countries competing to build new future colliders. So for Japan, for instance, has been planning to build the International Linear Collider. So which the feasibility studies show that it would be very important for Higgs boson precision studies, electroweak interactions, and more. In China, the Circular Electron-Positron Collider is going to be a Higgs factory. If it happens, it's going to run at 240 GeV center of mass energy. Precision studies of the W and the Z boson. And then the future circular colliders at CERN, which is supposedly going to be a 100-kilometer tunnel if it is built at all. So right now, feasibility studies are going on, but those are not enough. So people need to convince the various governments that these need to happen and need to present interesting cases why these need to be built. So I am hopeful that many of you in the audience will probably be able to show cases why we need future colliders in the like any of these future colliders. So FCCEE is going to be a precision Higgs machine like the ILC, and it will also be able to measure very precisely, like to a per mil level of precision, the properties of the W and the Z boson. So there are future hadron collider prospects. So this same tunnel will be replaced by proton beams in the very distant future. So it will be useful for direct searches for new particles which might be very heavy, which are not accessible at the Large Hadron Collider. It will help us study the Higgs potential very, very precisely. For instance, we know that the Higgs self-coupling is extremely tiny, so we can only measure the Higgs self-coupling through either di-Higgs production or tri-Higgs production. So di-Higgs production will be probed to a certain extent at the end of the run of the Large Hadron Collider, but tri-Higgs, it's extremely difficult because the rate is too small. So it's also like supposed to study the physics of the early universe. And then another future collider proposal is future muon colliders. So direct search for new particles with very clean collision environment, much cleaner than hadron colliders. So now I'm going to like slowly delve into effective field theories here. So why we need effective field theories, why effective field theories suddenly became so interesting at colliders. So I'm going to talk about model theistic versus model agnostic. So I'll tell you why this is model agnostic, so not exactly model independent effective field theory approaches. So I took this cartoon from Tim Tate. So here you see that like just for dark matter, there are a plethora of theories. There are so many different kinds of theories which can give rise to dark matter candidates. And this is not the complete picture. There could be many more. So why do we not want to study this any longer, or rather keep it as an aside and start talking about something somewhat more model independent? So no direct hints towards new physics, which explains the various observations like dark matter, existence of dark matter, massive neutrinos, more matter over antimatter, and so on, or physics beyond the standard model. So there are many models available to us, but there is no consensus like which model is the correct one. The reason is that every single model that we study comes with an additional baggage of many other particles, many other interactions to study. So until and unless we get to know all of this additional baggage, it's very hard to say like what kind of new physics we are looking at. So the questions that we ask is that like, is the new physics that we are seeking, is it hiding somewhere? Like just, we are obviously missing for various reasons, like we are not studying the proper channels, maybe we have not yet taken enough data, or is it just above the present experimental reach? Is it just above a few TeVs that the LHC is not being able to probe at the moment? So, or are the interactions with the standard model particles extremely feeble? So if that's the case, so we may never be able to discover these particles, or we may need a lot more data. So we don't know the exact reasons why the new physics has not been discovered yet. Another very crucial thing is that the theoretical and the experimental precisions may not be good enough at the moment. So it's possible that the experiments will reach even better precision, and that even from the theory side, we match that level of precision through, for example, higher order perturbative QCD calculations, higher order electroweak calculations, and so on. So imprints of new physics could show up as tiny deviations rather than like something very to the face. It could be some tiny deviations in standard measurements. So these could be hints So that's why it's very, very important to minimize theoretical uncertainties. So this whole school has been about effective field theory, more precisely standard model effective field theory. So I'm not going to go into a lot of it. So, but you have all seen that, like in standard model effective field theory, where the EFT is written as a linear realization, we have the standard model dimension 4 Lagrangian, and then we have operators in increasing orders of the mass dimensions. So Joydeepta has discussed this in great detail. So there are many approaches to effective field theory, like standard model effective field theory. So one is the bottom-up approach, where we do not know what kind of new physics we are looking for. So we are ignorant and we write down all possible gauge invariant operators, gauge invariant under the standard model gauge group. And otherwise, if we say that we know what kind of new physics we are looking at, then we take our favorite physics beyond the standard model scenario, we integrate out the heavy fields, and then we get a subset of these operators that we would have obtained had we taken the bottom-up approach. There's something called RGE equations. So for example, the operators that we get are at a cutoff scale of new physics. However, if we want to see, we want to study the picture at some lower scale, we would need to run down these operators, and we'll see some interesting things, like for instance, some of these operators would mix with each other. There might be new operators which would be created, and so on. So for example, L8C has not yet found conclusive evidence of any BSM physics. So there are usually two broad methods to study. So for example, model dependent, as I was saying, that take a model, preferably a UV complete model, and study all of its signatures very carefully. Otherwise, take a somewhat model independent approach and parameterize our ignorance as low energy effective field theory formalism. So the standard model, or any BSM theory for that matter, becomes a low energy effective field theory valid below a cutoff scale lambda. So this leads us to choose a set of low energy degrees of freedom, specifying the UV cutoff scale and the symmetries. So this is a cartoon taken from Francesco Riva, and here you see that the bigger theory which might be there is assumed to supersede the low energy model above this cutoff scale lambda, and the EFT effects can manifest themselves as deformations in various angular variables. So some kind of delta R, or like some azimuthal angle separation between some leptons, or some excession events in high energy tails. So because I said these will be in all probability very tiny deviations, we need extreme precision in theoretical understanding. So what is the standard model effective field theory? So it's an EFT which is constructed about the electroweak preserving vacuum out of the Higgs doublet phi. So Higgs doublet is the key phrase here, which linearly realizes the electroweak symmetry breaking. So the SMEFT can be written as a Taylor expansion about phi equals 0 in terms of operators in increasing mass dimensions, as I said. And the operators invariant under standard model gauge symmetry, which is SU3C cross SU2L cross SU1Y cross U1Y. And these are suppressed by powers of new physics scale lambda. So lambda for dimension 5, lambda squared for dimension 6, and so on. So for standard model effective field theory, when we expand operators, we see correlations between various deformations. So for example, let's take this simple operator H dagger sigma AH, W mu nu A, B mu nu. So this is the non-abelian W mu nu. And once we expand this, we see that we get interactions of the form Higgs with photons, effective vertex, Higgs with a photon and a Z, Higgs with two Zs, Higgs with two Ws, along with triple gauge couplings like two Ws and a photon, or two Ws and a Z, as well as the S parameter, which is the W mu nu, B mu nu. So from one single operator, we are getting so many different kinds of deformations. So if we take various operators, we get different kinds of deformations which we are able to correlate. So as an example, at the LEP collider, we were able to constrain the triple gauge couplings very, very precisely. So through the Z pole observable, so Z decays, and so on. So the thing is that even though the Higgs was not discovered back then, if the SMEFT structure is true, back during the LEP days, we already had information about the Higgs even before discovering the Higgs. So that's a very interesting thing that like this SMEF framework encapsulates. Before going on to the various discussions about SMEFT, something I just wanted to highlight which has not been discussed, probably Shubhoda asked me to just highlight this, is the Higgs effective field theory, or the HEFT. So HEFT is the most general parametrization of low energy physics with only the standard model degrees of freedom. So in this cartoon, in this way, we can show that like the HEFT will form a superset of SMEFT, which will form a superset of the standard model. So is there any scenario where only the HEFT can describe low energy effects of the BSM? So there are instances, and I have kept some in my backup slides. So later on, I would encourage you to go and look up scenarios where SMEFT is not going to be enough. So low energy interactions only follow the U1 electromagnetic. The interactions cannot tell us more about the properties of the microscopic theory. So new non-decoupling strong dynamics leads to spontaneous electroweak symmetry breaking, which leads to a Higgs-like scalar. So in SMEFT, what I told you before is that all these heavy physics, they are decoupled from the standard model, like they are at very high energy scales. But in the HEFT scenario, that might not be the case. So some of the particles may get some of their masses or part of their masses from the standard model, like electroweak symmetry breaking. So the standard model in the HEFT scenario is not recovered when all the BSM masses are taken to infinity. So in SMEFT, like if there is any non-analyticity in the Lagrangian, they could be waved away by field redefinitions, but in HEFT they often may not be. So this arises when new states are integrated out, they acquire masses from the electroweak symmetry breaking. So this violates decoupling. So unlike in the standard model EFT, where the premise was that the Higgs is a part of a doublet, here the Higgs is considered a gauge singlet of the SU2L, and the Goldstone bosons are an SU2L triplet. So, and these are treated separately, unlike in the standard model effective field theory. So the Goldstone bosons are actually embedded in this unitary matrix U, and the Lagrangian for the HEFT can be written down in terms of these. So it's a subset of the Lagrangian. So there's a Higgs term which is linked with the d mu u dagger d mu u. So Shotoda actually discussed this trace yesterday. So I encourage you to go back and see this, how to actually calculate this trace. And then we have the kinetic term for the Higgs, we have the Higgs potential, and then we have the Yukawa terms. So see here that unlike the SMEFT, all of these terms, this A, B, D, all of these parameters are independent of each other. They are not correlated. However, in SMEFT, at every dimension, these couplings are correlated, but in HEFT they are not. So these are the differences between SMEFT and HEFT. So SMEFT, for instance, is the most general set of local, it encapsulates the most general set of local operators which are invariant under the standard model gauge group. For the HEFT, its manifest gauge symmetry is SU3C cross U1 electromagnetic. In SMEFT, the operators are suppressed by powers of the new physics scale lambda, whereas in HEFT, they are suppressed by the electroweak breaking scale V. In SMEFT, the low energy states are modeled using fields transforming linearly, whereas in HEFT, these fields are transforming non-linearly using a multiplet of the Goldstone bosons. So the observed Higgs in SMEFT is a component of an electroweak doublet, whereas there is no relation between the Higgs and the Goldstone bosons in the HEFT scenario. So SMEFT has a more restrictive symmetry structure, as I discussed. There are less number of parameters which are correlated. The HEFT has a less restrictive symmetry structure. There are many more number of uncorrelated parameters. So now I'm not going to discuss HEFT anymore. So if you have any questions, you can ask me in the end. So the types of particle discoveries, or particle physics discovery. So this is the one that's been tested very well. So discovery through resonance, this is the tested paradigm through which we have discovered all the particles that we know of today, the resonance. However, as I said, that it's possible that we may not be able to find new physics at the LHC because it has been 12 plus years since the Higgs discovery in 2012, and we have not seen any direct evidence of new physics, especially in the high energies. So this new paradigm, as I said, is discovery through precision. So it could be discovery through some difference in angular observables or some excess of events in tails of certain distributions. So we would require percent or smaller level of precision in order to be sure that we are discovering something. So there are various types of uncertainties in particle physics. So I'm going to discuss a few here. So there are experimental systematic uncertainties, which include instrumental uncertainties, uncertainties due to calibration of energies, scales and resolution of detectors, and more. Then there could be experimental statistical uncertainties, which stem from finite number of events recorded. So the more number of events that we record, the less the statistical uncertainties become. And the systematic uncertainties are also being improved gradually by the LHC. Modeling of signal and background. So this is a theoretical uncertainty. So whether we do our calculations at leading order, next to leading order in QCD, next to leading order in electroweak, it depends completely at what perturbative order we calculate our theory modeling. That actually includes or some level of uncertainty encroaches there. So luminosity, uncertainty on precise determination of the rate of collisions, and then when we are doing some theory simulations through Monte Carlo simulations, we can also get some uncertainties from Monte Carlo simulation packages. So the aim is to have the theory precision and the experimental precision kind of match, so that it's not that experimental precision just continues to improve, and we are stuck with our experimental precision at some level. So now I'm going to discuss a few examples only. So taking from what Shubhoda discussed yesterday, so he discussed the Z Higgs scenario. So I'm going to discuss the V8 scenario, and I'm going to give you some perspectives of how to do collider physics. So this could be an example from where you can start. So for instance, here I have the beam axis, so two protons collide, and what it produces is a Higgs boson and a gauge boson, or rather a weak boson. So it's a W or a Z boson. So for the Higgs scenario, I consider it decaying to a pair of bottom quarks, which become bottom jets. And because the Higgs is a scalar, for now I'm going to look at the Higgs decay as something called a fat jet. So I'm not very much keen on looking into the angular structure of the decay products of the Higgs. So this would actually improve the analysis further, but let's for now look into the decay of the weak boson. So the weak boson in its rest frame decays to a pair of leptons, L1 and L2. So for a Z boson, it would be an L plus and an L minus. For a W boson, it would be a charged lepton and a neutrino. So what we do is that, so I showed you three angles. Look at these three angles. These are going to be important. So there's a big angle theta, a small angle small theta, and then there's an angle phi. So these phi and big theta, and this XYZ coordinates, the X, Y, and Z coordinates, are in the V8 center of mass frame. So V and H. So it's in the center of mass frame of the V8 system. So and the theta is in the center of mass frame of the V. So the rest frame of the V. So in order to have relate these theta, small theta with the big theta and the phi, we need some Lorentz boosts. So we would need to boost one to the frame of the other in order to do analysis. So how much differential information can one extract from this process? So for three body phase space, so we are taking the Higgs as one body and these as two bodies. So it's a three body phase space. We have 3 cross 3 minus 4 is equal to 5 kinematic variables, which will completely define the final state. So barring the boost factor, as I discussed, there will be a boost factor. The variables will be the center of mass energy and these three angles. So I'll show you in a bit. Once we write down the amplitude of the PP to VH and the V decaying to a pair of leptons, we square the amplitude. What we end up with are these 9 angular structures. So you see that these angular structures are functions of this big angle theta, this small angle theta, and there's also phi here. So these are the three angles. So if we write down the amplitude squared, we get these 9 structures. So these are the only 9 structures which come about, and a very nice calculation has been done by Hitoshi Murayama and collaborators before, where they show that how many angular structures are going to be present for every dimension operator for every process. So it's a very interesting paper that you can look for later on. I can actually link it later on when I put the slides up for upload. Sure. Oh, yeah.
So then we have in amplitude square can be written depending on these three variables: capital theta, small theta, and phi.
Yeah.
And in third plate we have kinematic variables, 5 kinematic variables.
Yes.
So is it somehow 5 kinematic variables are termed in terms of these three variables?
No, these 5 kinematic variables are these 4 and the boost factor. So these are the 4 kinematic variables, and I have not written the boost factor here. So those are the 5 kinematic variables that we are talking about. So yeah, so I'll show you how I squared these amplitudes and how these come about in a bit. So now I just wanted to compare two processes. So I talked about this VH production, and probably many of you have heard that the Higgs was discovered through the ZZ star channel in 4 lepton final states. So Higgs was first discovered in 2 channels, the diphoton channel and the 4 lepton channel. So this is the 4 lepton channel, and here the angles look a bit different. So one of the two Zs is an on-shell Z, the other is an off-shell Z. So there are 2 angles, theta 1 and theta 2, and there's another angle phi. So these look a bit different from these thetas here. However, even when we squared the amplitude here, we see that we end up with similar angular structures for the gluon fusion channel as well. So we get 9 angular structures here and 9 angular structures here, which are not exactly the same. And I'll show you something interesting is that, like, some of these terms, you will see that they come with squared powers of these trigonometric functions, and some of these terms come with just linear powers of these trigonometric functions. So when we finally do the phase space integration, the terms which have linear powers in the trigonometric functions, they actually become 0. And so there should be a way that we do not lose those terms. So I'll discuss those, because you will see shortly that in standard model for such processes like Z Higgs, W Higgs, the longitudinal term actually dominates over the transverse term, because the Z could be longitudinal as well as transverse. So the longitudinal terms dominates. However, in the effective field theory scenario, we often have some of these couplings only as an interference between the longitudinal and the transverse, which come with these single powers of cosine thetas, sine thetas, and so on. So if we integrate these out and these vanish, then we completely lose information about these terms. So there's something called interference resurrection, through which we can actually make these terms non-zero. So now let's discuss VH production at colliders. So this is 2 quarks through a W or a Z mediator producing a W or a Z boson with a Higgs. So you see that here I've given 3 diagrams. So the black dots basically symbolize that these are vertices which are affected by the effective field theory operators. So when we, as I wrote before, that when we expand these effective operators, we get these interactions to be dependent on the Wilson coefficients of these operators. So these operators actually give rise to deformations in various interactions. So here we see that there are 3 kinds, and the third kind is particularly new because this diagram is not there in the standard model. It's a 4-point interaction, which we'll see that it grows with energy. So here I have already showed you this diagram. So I also told you that this could be made more differential, and I have told you that for the Z Higgs, once we square the amplitude, which I'll be showing shortly, it's possible to probe multiple angular observables at the L8C. So the L8C can actually see many of these angular distributions, and rather than just studying some cross section or some PT distribution or some azimuthal angle of some leptons, we can actually study these 9 independent angular observables, and we can constrain many EFT directions. So there are many operators which contribute to such deformations, but in the Warsaw basis, all the dimension 6 operators are these. So these are all the operators, and you can look up these operators. Many of these operators have been discussed in previous talks, in Shubodha's talk and so on. So there are also CP odd operators. So we do not only get to constrain the CP even operators, but we also get to constrain the CP odd operators. So whether there's any presence of CP odd structure in the couplings at all from the present data. So now what I do is that I write everything in the broken phase. So I write the Lagrangian, not just, so don't focus on the entire screen, focus on these 4 blocks, and I'll be discussing what these 4 blocks are. So I discussed what these 3 diagrams are. So when we take all these operators that I discussed here, we open these up, we expand these up, we are able to write down these terms. So the terms in blue are basically very similar to what the standard model terms look like. So here you see the Higgs Z mu by 2. So this is exactly what the standard model term looks like, but it comes with a prefactor. So this is basically standard model term with a scaling. It's called the kappa framework. So in the initial days of the LHC studies, more differential terms were not considered, and only these scaling modifiers were considered. So in some of my initial studies, we only considered these coupling modifiers, which only scaled the couplings but did nothing else. But since then we realized that we could do much better. So we could actually study some new structures, look at the black blocks for instance, which do not arise in the standard model. So for example, Higgs Z mu nu, this is a CP even term with a new Lorentz structure, new with respect to standard model. And then we have a Higgs Z mu nu tilde, which is basically a CP odd term with a new Lorentz structure. In standard model, there are no such CP odd terms at all. So both of these terms are missing in standard model. So these terms actually come from these kinds of interactions. And then we are met with this contact interaction. So see here, it's a very weird looking term, Higgs Z F bar F. So it's a 4-point interaction, which is basically this one. So 2 F's, a Higgs and a Z or a W. So these are the 4-point interaction. So here you see that because it's a 4-point interaction, then there is no propagator suppression here. So whenever there is a propagator, there's going to be a suppression, but there's no propagator here, so there's no suppression. So this grows with energy compared to the other terms. And I have listed here 4 couplings. Just look at here, this circled one, delta GZF. So these are the 4 directions that I'll be discussing, which are called the so-called high energy primaries. So I'll be discussing that at high energies, so of these many operators that I discussed, only 4 operators will be surviving. The others will not contribute at all. So, and all of these 4 operators can be encapsulated in this coupling. So this F actually is like it hides the indices, so it would be up left, up right, down left or down right. So there are 4 kinds of couplings here which are hidden in this one coupling. So this, let's forget about this slide. So here I have written down everything in the broken phase. The reason for writing in the broken phase is that when we are talking to experimentalists, we don't want to impose on them what kind of basis that we are choosing. So we could be working on the basis that has been discussed a lot of the times in this workshop, the Warsaw basis. There's something called a strongly interacting light Higgs or the Silch basis. There's something called the Higgs basis. There are many different kinds of bases that particle physicists usually work with. So we don't want to like impose on experimentalists with so many details because they are already doing a lot of analysis. So what we can do is we can write things in the broken phase. They can give us constraints on these couplings, and then we can map it on to the favorite operator basis that we want. So for this case, for example, in the Warsaw basis, this is the map. So you don't have to go through this. So now talking about the high energy primaries. So there are 4 channels, the Z Higgs, the W Higgs, the WW and the WZ. So even though these 4 processes look completely different from each other, they can be expressed at high energies respectively as the gold stones. So the Z becomes the G0, the W plus minus becomes the G plus minus, and so on. So all of these processes can be intertwined. So for example, the Higgs doublet can be written as this, G plus H plus Ig 0 by 2, and we'll see that at high energies, these four completely different processes, Z Higgs, W Higgs, WW, and WZ, actually become correlated. So the same set of operators actually relate all these four processes. So these completely different looking processes, just understand this, can be like constrained in the same parameter space, and we'll be able to constrain the same parameter space by studying these four processes. So they are intrinsically connected by gauge symmetry. So this is, I highly encourage you to read the Goldstone boson equivalence theorem. So it's a very important fundamental thing that comes in quantum field theory. It is possible to compute amplitudes for various components of the Higgs in the unbroken phase. So Shottoda discussed like very similar things yesterday. So I encourage you to go back to it and study his notes. So he discussed about he discussed it in the global scenario. However, when we gauge a scenario, the Goldstone boson equivalence theorem might look slightly different. So whether you're choosing the Arzai gauge, whether you're choosing the Feynman gauge, it might look a bit different. So high energy primary. So I was just talking about these four processes, the WZ, the W Higgs, the WW, and the Z Higgs. So see that there are these four processes, and there are different initial productions. So for example, UD, UU, DD, and so on. So there are left-handed particles for the up and the down, as well as the right-handed particles. And these are all combinations of these four high energy primaries, only these four. So at high energies, these four processes are linked only through these four high energy primaries. And you'll be able to write these four high energy primaries through the couplings that I just discussed a while back, these couplings, these four couplings. So it's very interesting, even though you are probably not be able to grasp all the nitty-gritty details of this, but know this, that like using the Goldstone boson equivalence theorem, we are able to relate four completely different processes. And yes, VVF is also, it's basically the fifth process which can be tested with this. So I'll show that in one of the later slides. Yeah. Sure.
So as you discussed this SMEFT, difference between SMEFT and HEFT.
Yes.
And you have these vertices like HJZ vertices.
Yes.
And it is suppressed by inhaled by V, electric wave.
Yes.
And in SMEFT, it could be like lambda square, maybe.
Yes. In dimension 6 lambda squared. If you
Yes.
go to higher dimensions, then something else. Yeah.
No, even if one consider, let's say, lambda order of TAV,
Yes.
then ZH production in SMEFT will be much smaller than this heft.
So it depends on the size of the coupling as well. We haven't.
Let's say for order 1 coupling.
Yeah. So exactly. So it will be smaller. Yes.
But it should be same, right? It should have be same.
Because it depends. So as I said, in the heft scenario, we have a non-decoupling regime. So in the SMEFT scenario, we have a completely non-decoupling regime. So the couplings will not be the same. So for the heft scenario and the SMEFT scenario, you cannot choose the same coupling. So when you are choosing a different scale, the couplings you'll not be able to choose the same couplings for the case.
that means in heft scenario, this coupling order of very small, like order
Yes.
-3, -4.
Exactly,
Like.
exactly. So you can map these two completely, but in a non-decoupling scenario only. Was there any other question? Okay. So here basically, as I said, through the Goldstone boson equivalence theorem, you are able to relate these four processes exactly, and as Tisha mentioned, you can also relate the weak boson fusion channel through the Goldstone boson equivalence theorem because you have the same vertex there. So you either have the WW Higgs vertex or the ZZ Higgs vertex. So now we can actually map the high energy primaries to the low energy primaries. So I told you that in effective field theories, when you expand out an operator, you get many correlations. So you get some correlations between the Higgs couplings and the triple gauge couplings or the Z pole observables. So here you can see that the high energy primaries can actually be linked to the low energy primaries, the four couplings that I've been talking about. So these are the four couplings that I've been talking about, this delta GZF, and here you see that I have written them as delta GZUL, DL, UR and DR. So all of these couplings can be written down in terms of these 4-point Z pole interactions as well as the triple gauge couplings. So this delta GZ1 is basically the interaction between two W bosons and a Z boson, and delta kappa is basically the interaction between two W bosons and a photon. So what I'm trying to say is that at high energies, you can map your observables to low energy primaries as well, because these were measured at LEP. LEP was a much low energy machine than L8C. So you were able to constrain these couplings at LEP very well. However, these couplings which grow with energy, you will only be able to constrain them at very high energies. So high energy couplings are linked with the low energy observables as well. So that's basically what shows that the high energy primaries can be linked with the low energy primaries very, very intimately for these four processes, which are linked through the Goldstone boson equivalence theorem. So as I said, that we started with a lot of operators. So we started with 18 different operators for the weak boson, for the Z Higgs and the W Higgs. But once we go to very high energies, of these 18 operators, 14 of them are no longer important. They don't grow with energy, but these 4 operators do. And we are able to link these 4 operators to the high energy primaries that I have been talking about since the last 3 slides. So this AQ1, AQ3, and this AUR and this ADR. So you see that AU, AD, AQ1 and AQ3 can be actually related one-to-one with these 4 Warsaw basis operator coefficients. So now coming to the Z Higgs production, I am going to discuss a bit about helicity amplitudes and how you do the calculations. So in case you are interested in doing the calculations. So here you see that for a 2-to-2 process, say a fermion with a helicity sigma and a fermion bar with minus sigma giving rise to Z Higgs, the helicity amplitude can be written down as, so for the transverse part, we have this expression, and for the longitudinal part, we have this expression. See here that the transverse part is suppressed by an additional factor of 1 by square root of S hat. So that means that these terms 1 and 1, these are the standard model pieces. So just when we take the standard model part, the transverse part is way smaller than the longitudinal part, especially in the high energy regimes. However, when we take the effective interactions here, so we write down all these operator coefficients which are hidden in these couplings, which I showed you a little while back, we will encounter scenarios where even the transverse part can become large, because you see that it comes with an S hat. So this S hat will actually cancel out with this root S hat, or so there will be energy growth even when we take the interference between the longitudinal and the transverse pieces. So when I take this amplitude, so this amplitude is only for the 2-to-2 process, then what I do is that I include the Z decays. So then I have all the 3 angles, the big theta, and remember I discussed about the small theta and the phi angle. The small theta was basically in the Z frame, how the Z decays to a pair of leptons, and the phi was basically the angle between those 2 planes. So then what we do is that when we square the amplitude, we get these 9 terms. As I was talking about, these 9 angular structures we get very clearly from there. And these coefficients sitting here are actually functions of these EFT couplings as well as the energy. So we can actually write down the squared amplitude, we can decouple the energy piece from the angular pieces, and we can do our study. Yes?
So like we do we construct these 9 observables for Higgs style process.
Yes.
Can we do for vector boson fusion by
Yes.
taking jets in as frame and
For the weak boson fusion, it's going to be much more difficult in the sense that there's like the Higgs is going to decay into something, and there are 2 jets which are not related to anything else. So you have to take many more angles there. So there will be many more angles at play. It's definitely doable, but it's not going to be, so it will not be these 9 angular observables. There will be something different completely. So you have to do and check it out. So I'm repeating this picture once more because this will come back again and again. So as I said, there's this kappa framework, this scaling, and then this contact interaction, and then there are these new Lorentz structures that we talked about. So EFT validity. So till now I have not talked about EFT validity at all. So till now we have been talking about some Wilson coefficient, say C, and some scale, say lambda. So we have been talking about constraining some C over lambda to the power something. But what if we are doing some EFT with some UV matching? So again, I encourage you to look at Joydeep Das talks slides again. So when we try to do some matching, then this EFT validity question becomes even more important. So for example, we can take a very simple case that we can have an SU2L triplet and a singlet vector W prime and a Z prime, which couples to the standard model fermion current. So this is the triplet current, this is the singlet current with a coupling strength of GF, and to the Higgs current like this, I H dagger sigma A d mu H for the triplet case, and this is for the singlet case with GH. So when we integrate out the heavy fields, so again integrating out probably has been discussed in the school, or else like just ask me, I'll be happy to include those in my slides. So you see here that we are left with effective couplings like this GHZ U or D L and GHZ UR or DR. So in these couplings, some of the couplings are known to us. So for example, G is the standard model coupling, V is the standard model VEV. So we know the G and the V here, we do not know the GH and the lambda. So if we assume some weak coupling, for example, if we take GH equals 1, for instance, so in standard model the G is of the order of 0.3. So if we take G of the order of 1, then we have a strong constraint on lambda. So then in our EFT analysis that we do in colliders, we cannot go to like arbitrary high energies in our analysis. So that's what I show here next. So here you see this cutoff line which we calculated event by event, and we found that this is the cutoff for the Z Higgs invariant mass. So you cannot take any events above this cutoff scale when you choose some coupling. So had you chosen a different coupling, GH equal to 0.5, this line would have been different. But once you stick to a coupling, then you have to basically throw out events which satisfy this kind of a scenario. So, but yeah.
Also, like moving to the lambda.
Yeah.
The lambda is far away from the electric scale.
Exactly.
Then the RG could play very crucial.
RG could
decoupling.
absolutely. So RG could actually. So I don't think I'll have time to go to the RGs, but it's there in the slides. So when you use the RG evolutions, so you see that many of these operators run down to certain scale, and there are like very intricate dependence on this scale, and there are some logarithms which come about. So this lambda becomes even more interesting when you, this cut EFT validity becomes even more interesting when you take into account the RGEs. So here what I have done is that this is the collider study. This is an example of how you do a collider study. So what you do is that you basically, here we studied Z Higgs process. So PP going to Z Higgs, we let the Z decay to a pair of leptons and the Higgs to a pair of B quarks, which became a fat jet. So what we did is that we had to take all the relevant backgrounds. So the backgrounds that were important were Z BB bar, where this BB bar doesn't come from a Higgs, a TT bar, and a fake background of Z going to 2 jets. So in collider analysis, fake backgrounds are often important because detectors are not always able to understand with 100% certainty whether a jet is coming from a B quark or a C quark or a light jet. So when we tag a B jet, so some of you may have read about tagging jets. So I'm not going to discuss how you do tagging for jets. So when you tag a B jet, it always comes with a certain probability, like some 60% or 70% of the cases, you can say with certainty that this B quark has become a B jet. So, but for other cases you cannot, so you lose a lot of events. But it's also possible that it didn't originate as a B quark, it came as a light quark, but it faked as a B jet. So that's also possible. So the more the fake probability, the bigger the background is going to be. You have a question? So it's important that the experimentalists study and reduce the fake backgrounds to the maximum level possible. So they do that. So we include all of these backgrounds and we do a collider analysis. So this is something called a cut flow table. So basically we in a collider analysis we require certain steps. So basically we require that there is going to be one very fat jet with a radius of 1.2 where there are going to be 2 B meson tracks inside. Then we require that there are going to be 2 opposite sign same flavor leptons, because we are having a Z boson here. So the Z boson decays to an electron and a positron, or a muon and an antimuon. So we have 2 opposite sign and same flavored leptons, charged leptons. Then we require that the Z boson, actually the 2 leptons, we reconstruct them and they peak at the Z boson mass. So that's why we require that the invariant mass of the 2 leptons peak around the Z boson, and so on. So we require all of these cuts, and we see that for the signal we get certain efficiency. So with every single cut that we put, a certain number of events they are thrown out, that they are not included even for the signal. But we must ensure that whatever cut we are choosing, the signal's efficiency is much more than the background's efficiency, because our aim is to reduce and remove the backgrounds as much as possible. So this is basically the framework how a collider analysis is done. I don't know like how many of you have done collider analysis here. So the first step is basically, so I have not included the first step. The first step is to write down the Feynman rules and create a model which basically helps us do the analysis. So we do an event generator which generates the hard process. So it's either the 2-to-2 process that I talked about, the PP going to Z Higgs. It includes the resonance decay. So the Z boson is decaying to a pair of leptons. And then we also do something called the PDF sampling. Then we have the next step called the parton showering. So the initial quarks which are in the picture, or the gluons, they can shower. So the quarks can actually shower into photons and gluons. The gluons can shower into gluons. And the final state particles can also shower, which are called the final state radiation, or FSR. Then we have a step called hadronization, where we form the baryons, the mesons. Then we have a step called underlying events. Then we do the detector simulation as I discussed here. And then finally we do the event reconstruction. So we identify the particles, whether the particles are leptons or photons or jets or some missing energy or so on. And then we do something called a jet clustering and so on. So have a look at this if you have any questions. So it's very short time to discuss this, but I'll be very happy to take your questions later on. So, oh, this graph didn't come at all. So there's a gray blob here. So what I was going to say is that because of the Goldstone boson equivalence theorem, I told you that these 4 processes, W Higgs, Z Higgs, WW and WZ, they're all connected along with VVF. So you see that we can map these 4 processes into the plane of the triple gauge couplings. So I told you about the high energy primaries and the low energy primaries. So remember here we discussed the high energy and the low energy primaries. So these processes, the WH, the Z Higgs, they can be mapped onto the low energy primary parameter space as well. So here you see that the same processes, actually Z Higgs, WZ, they all fall in the same parameter space. So LEP had already constrained this process, these processes, and the region was supposed to be this big. And now through L8C, we are able to constrain this very, very narrow region. So L8C actually improves the precision by orders of magnitude. So without cuts, we had the signal over background to be around 5 over 160. And then we did something like called a cut based analysis, a regular cut based analysis. And we found that the signal over background became a quarter. So from 5 over 160 to a quarter. And then we used a machine learning algorithm, a boosted decision tree, a primitive machine learning algorithm, and we improved the signal efficiency or the signal over background from a quarter to a half. So that is the power of including machine learning tools in collider analysis. And you see here that many of these couplings were constrained at LEP, and then one was able to constrain them even better at the L8C And if the FCC is ever built, these constraints would become sub per mil. So we want, as I was saying, we need a lot of precision. So sub per mil precision would be available. We'll be able to achieve those at future colliders, but even per mil precision is going to happen at the end of the run of the L8C. So I discussed the contact interaction here. So here basically I included the 4-point interaction, this one, but I didn't talk about these angular observables yet. So in the same vein, we can do the analysis for the angular observables, and we can see that we are able to constrain the angular couplings, this kappa ZZ tilde and the kappa ZZ, to the order of 1% or even stronger. So we are able to constrain the CP odd couplings as well as the CP even couplings. I'm not sure how well this is visible from the back, but know that collider analysis are able to constrain these couplings to percent level or better. So we need even more precision in the future, and we see here that the experimental collaborations usually take a single operator at a time and do their analysis and give some bounds, but it is important to take all the relevant operators at a time and do the bounds and present the results. And we see that once we do that, one can achieve even better bounds than what the experimental collaborations give us. So Shubhoda, how much time do I have left?
3 more minutes.
Okay, so I'll not go into the WW channel, for instance. So I'll just like close with the theory uncertainties in EFT analysis, which are very important. So for example, I think Joydipda and others have covered bits of it. So theory uncertainties in EFT analysis. So there could be ambiguities in operator coefficients. So for example, when we take a dimension 6 operator, do we keep only the linear term? Do we keep till the squared term? Or do we take dimension 8 operators? So that is an ambiguity that leads to some uncertainties. Similarly, validity of perturbative expansion is another source of uncertainty. This is what Joydipda was saying. The RG evolution effects alter the behavior of the theory. So this describes how EFT couplings vary with energy scales. So EFT couplings, when we say that we have constrained the EFT couplings, the answers are at a fixed scale. When we want to know the results at a different scale, we need to use the RGEs. So these are in the later slides, so you'll be able to see these. And there can be inconsistencies while matching to a model. So whether the SMEFT is a good approximation or the HEFT is a good approximation, this all depends on the kind of model that we are trying to match with. Also, at what order we are stopping. Are we stopping at dimension 6? We are stopping at dimension 8, and so on. So I'm not going to go through these slides, but there are some interesting slides. You'll see that how next to leading order effects, I didn't actually intend to cover these, but how next to leading order effects can become very, very interesting and important. So I'm just going to flash a result for WW. So whether we take a QCD correction to our backgrounds and whether we take a QCD plus electroweak corrections to our background, the bounds can actually change significantly. The reason is very, very simple. For WW process, you see that even in the standard model, the cross section decreases significantly with very high energies. So that is because there comes about some negative Sudakov factors which makes these cross sections very large. Usually the collaborations don't include such electroweak corrections, or even theorists don't include such electroweak corrections. But for gauge boson, dye boson production, or any electroweak processes that we study at L8C at high energies, it's invaluable. If we do not consider the electroweak corrections in our studies, we get bounds which do not make much sense. So that's what I'm showing here, that we can see clearly that by taking or not taking the electroweak corrections to the backgrounds, we get completely different bounds. So I stop here, and I would encourage you to join the L8C EFT working group. So this is a clickable link, so you can all join, and we have monthly meetings there. So if you have any interesting idea pertaining to EFTs, you can let me know or let the other conveners know, and we'll be happy to include you in some of the discussions. So we have topical discussions every single month. So thanks a lot once again. Yeah.
sometimes people write most general structure of couplings instead of writing EFT operators
Yeah.
and then obtaining.
Yeah.
Although those structures can be obtained from EFT.
Right.
And the CMS Atlas
Yeah.
papers also published.
Yeah.
Means their studies also based on those most general structures.
Right.
Is it because those means that approach is more relatable with experiments, or maybe one of them is more applicable to classify models?
Yeah. So this approach used to be like in the vogue with CMS and Atlas before we formed the EFT working group. So because experimentalists did not think about this, so they wrote all possible modifications. But the thing is that all these modifications do not, when we do it from an EFT perspective, all these modifications do not happen at the same order. So from dimension 6 you get some structures, from dimension 8 you get some structures. What they used to do is that like they wrote all structures which would come from an addition of all dimension operators. So that is no longer encouraged by the EFT working group, and experimentalists are slowly phasing it out.
One more thing. So, in addition to why we want to study higher dimensional operators, we are not limited to just Kappa framework, because of we want to go more on deeper understanding of new physics, right? But if we are limited to Kappa framework, then in NLO corrections, Kappa framework doesn't allow UV cancellation.
It won't, because it's not gauge invariant.
Okay.
So unless you write all the operators, the study is completely not gauge invariant.
That's
so
why we need.
yeah, you need to include all operators, especially for loop calculations. I think people are tired.
Okay, so if not, let's thank Shankho for a wonderful talk. And I have the privilege to do the honor to felicitate him with a traditional gamosa and a piece of memento.